So today we're going to be going over how to make a part in SolidWorks and then convert it into CAM. So you can plug it into a CNC machine and have that machine make the parts. So first we need to model a part, and it's really important that we pay attention to what planes we're using. So let's just make a 2x1 with some holes in it. So let's do right plane, and we'll sketch on that plane. And we'll make our rectangle. Make this our 1-inch face. Make this 2-inch face. We'll select all our edges and offset entities. Make it 1/8 of an inch. Wall thickness. Okay, and then we'll exit that sketch and extrude that. I'll do it from the midplane. And we'll make it, I don't know, 24 inches long. Okay. Next we'll want to put some holes in it, so we'll sketch that. Put our hole, smart dimension, make it the right size. It's going to be 1/2 inch from here and 1/2 inch from here. 1/2 inch. Okay, we'll exit that. We will extrude cut that hole. Make it through all. Okay, looks good. And then we'll take that and we'll pattern it in this direction. Now normally this is spacing and instances here by the default, but we're going to use up to reference. And we're going to pick this to be our reference that it's going to pattern up to, and we're going to change our spacing to 1/2 inch. And we don't want that last hole there, so we're going to change our offset to 1/2 inch as well, so it won't put anything within 1/2 inch of this edge here. And then for our second direction, we'll do the same thing. We'll pick that. We'll pick this direction. Clear that. We'll pick this direction, and that'll be up to here. And again, it's a 1 inch this time, so it's a 1 inch pattern. And it looks like we don't even need to set an offset for that one, so we'll leave that. That looks good. Okay, and we can do some holes in the top as well, so we'll do the same thing. We'll sketch, put a circle, do one. It's going to be 1/2 inch from this edge and 1/2 inch from that edge. Okay, we'll exit and extrude cut through all. Alright, and then we'll go ahead and pattern that as well, the same way. Looks like it kept our settings, so we don't need to mess with that anymore. Oh. Okay, you need to change our reference. So our reference will be here. There we go. Okay. And you set an offset as well. Didn't keep our offset. Alright, that did it right there. Okay, so we've got our part now. And we want to we have this part made, right, for the bot, and now we need to move it to the CNC so we can actually make it, manufacture it, and get it onto the robot. So to do that, you all should have installed HSM Works or HSM Express. We're going to go to CAM. Now this is a whole different tab up here with all of its own different stuff, and we're going to look into all this in this video. So what CAM lets you do is it lets you take this part that you've made and go directly into transforming it into what's called G-code. And that G-code is what the CNC machine reads in order to create parts. Right? It reads that G-code, and it's a set of operations that the machine needs to perform in order for it to machine this piece of metal. An important thing to understand is that there are 4 individual faces on this part that need to be machined, and our machine can only do one at a time, so you have to do a program for the top, bottom, which in this case they're the same, so you only need to do the one, and the left and right, or whatever orientation this part happens to be in. I guess this would be left, right, top, bottom, back, front, if our planes, right? So that would be the front, that's the top, that's the right. So from here we need to make a job, and that job will use this model, and the stock will use a from extruded sketch. And from the extruded sketch we will go ahead and pick our original sketch that we made, and that's all we got to do. And then from here we'll do stock offset of 0 and a height of 1 inch should be fine for this. Does it pick up the right place? Okay, we want to change that to the same length. And let's look, going to change our offset because it went from the center, so we'll change it to half of what our height was. Okay, so now our stock fits inside of our model, so that's good. Now this is the important stuff right here, is our stock orientation and our work coordinate system, because this is what the CNC machine is going to establish as a 0, and it needs to know how this works in order for it to know where anything is at all. So we'll need to go into our zeros and find where our 0 is. So we'll use for this one use X and Y axis, and it really doesn't matter just because of how symmetrical this part is, but let's pick this back corner as our and it's really distracting. These are still showing up in blue, but we'll select our x-axis will be the long end of the part, so this will be our long end, and our y-axis will be this short end. And our z-axis, which is the blue one there, you can see down here, right? X is red, Y is green, and Z is blue. So that looks right. That is the correct orientation, because really we want the x-axis to be the long end, because that's the way the machine is designed, and we want the y-axis to be the short end, and the z-axis is just up and down, so that's fine. And then for origin, we will do a selected point, and we will select this. It has to be this back corner. It has to be the left corner of your model because of the way the machine is built. Oh, I'm sorry, I just moved our y-axis. Let's change that. So that's our y-axis, and our selected point will be this. Okay, so that's good. That looks good right there. And that's it. That's all we got to do for job. That's done. Now we can start adding operations. So really, what do we have to do on this part? Well, obviously we have to bore all these holes out, but then we also have to do, what would be nice is if we could trim up these edges, because when we cut them with a saw, it's not that great looking, and it's not really all that straight. So if we trim those edges, we can get this thing to the exact correct length, to the thousandth of the inch, and at the same time clean up that edge so the finish looks better and everything fits together much nicer. So we'll go ahead and do both those things. So we will go ahead and do a 2D pocket operation. Now this is where stuff gets a little complex. So you see all these numbers here, and we really can break these down pretty easily. But first we need to pick a tool. Now our tools that we have available to us is pretty simple. All we have is this flat number 4mm end mill, which we can all program in. Help you guys program in later. It's not that hard. Actually, we can make a second one right now. So we'll do a new mill tool. It'll be number 2. Its length offset will be 1. Really, this truly does not matter all that much. Material will be carbide. Manual tool change, and that can stay like that. Cutter. The diameter is 4mm, so you can just type that in and it'll give you what that is in inches. There's no corner radius, so put 0 for that. The shoulder length, none of this stuff really matters because we don't use any of that. Options, make it a flat mill. There you go. Okay, flat mill, and then diameter. Shaft really doesn't matter. Holder doesn't matter. Holder doesn't matter. Feeds and speeds. You want to set this really at around 18,000 RPM. So 18, 1, 2, 3. And number of flutes, 1. You want to change your cutting feed per tooth to 0.004 inches. And our anywhere from 0.004 to 0.003. 0.003 is actually or 0.035 might be better. We'll take a plunge feed rate. I want our feed per revolution on the plunge to be 0.002. It's nice and thin. So you may be wondering what this feed per whatever is here. What it is basically is that we've got this thing rotating a certain number of times per second. And for every revolution, it's going to advance 0.02 of an inch downwards on the feed. So as we're feeding downwards, it's going to advance 0.02 of an inch per revolution. So the tool, its one tooth, is going to take off 0.02 of an inch per revolution. And then when we're cutting, like sideways, right, we're going to be cutting 3.5 thousandths per tooth. So each tooth is going to take that much, 3.5 thousandths. Now if we had more teeth, like 3 or 4, we could move much faster because we'd have more teeth that each take that much out at a time. So that's what those mean. And then lead-ins and lead-outs, all that means is when the machine is leading into the material, so when it's spiraling down into the material to start cutting, and lead out is when it's spiraling back out or just plunging back out of the material. Spindle rotation is always clockwise. It's never counterclockwise. That's really all I need to know. Oh, surface speed, that's basically the speed at the edge of the tip. So how fast is the tip moving? If it's a really small diameter, but a really high RPM, it's gonna be something big like this. If this was like a 1/2 inch end mill, this should be much larger because it have a much larger outer diameter, and so the edge of it would be moving a lot faster. So that's all I gotta do with that. And so yeah, but we'll just use this one because this is the program. This is already the profile I have. So we'll select that one. You'll see it changes all this. So really, you don't even got to worry about it. Once you've done the tool thing, it basically settles itself. And now the selected contours. So this is going to be basically what you're cutting with this operation, this 2D pocket. Now, I don't feel like selecting each individual one of these holes by clicking on them. So what we're going to do is we're going to select the front, the bottom, and then we're just going to We're just going to drag. And it should pick up all those holes for us. Might take a minute. Yeah, okay, picked it up, all those holes. And then we'll just go ahead and deselect this edge. If it will let us. Come on, okay. Looks like it picked up the bottoms as well. That's what we don't want. Okay, so we'll just go ahead and go here. Oh man. Clear. We'll go to the bottom again. And we'll just barely touch. There we go. That looks like it's, yeah, there you go. That's more like it. And then we'll just go ahead and deselect whichever one of these is this edge. I'm having trouble finding right now. Okay, 150. Okay, there we go. 154 is what it was. All right. So we've got all these holes now, and well, that's it for that tab. That's all we got to do. Now heights. Heights is basically where you pick where you want the tool to start. So the top plane here is your clearance height. It is where the tool will go to when it's not cutting. When it needs to move around the top of the part to get to a new hole, it's going to retract to this height right here. It's going to go to here. So it's going to drill, come out to that height, and then move to the next hole. This retract height is where the machine is going to move to when it's just going to wrap it over to the next hole. This is like for long movements. This is for short little movements. This retract height here. Feed height is the same thing as the same distance right now as retract height, so you can't see it. So we'll change it. So it's this green one right here, and that is when the machine will start feeding downward. So it'll stop the. So there's 3 methods of movement for this machine. Is rapids, which is like the name says, it's just moving really fast to get to the next place as fast as possible. And then there's also cutting, which is, again, name's pretty obvious. It's just the speed it's moving when it's cutting to maintain the optimal feed per tooth. And then there is also the ramping. So it's ramping into the part, and that ramping starts at this feed height offset. So it'll wrap it down to here, and then it'll start feeding. And then this top will define the top of the cut is now it's what it's talking about. Top of the cut is 0 inches from stock top, which is correct. We want to start at the top of the top of the part here. And from the contour we selected, we want to go down negative 0.15 inch. Now, the reason we're not going exactly 1/8 of an inch is because we want to overcut. Because when we overcut, that means that we will, definitely break through the material. If this was solid underneath, if this wasn't like hollow, we wouldn't overcut because we wouldn't want to, mess up any other features. But since it's hollow, you can overcut by quite a bit. Really, the sky's the limit. I mean, until you hit the bottom part of the hole here, really, it doesn't matter. But yeah, because the machine bed isn't entirely flat, the machine will go to that exact depth every single time, but because the machine isn't flat entirely, because, it's got a wooden bed, it's not the best for doing exact depths over a distance like 24 inches. So you overcut slightly to make sure you punch through every single hole. Next is the kind of how you want the cut to work. So this tolerance you'll always set to 1/10,000th. So tenths, hundredths, thousandths, 10,000ths, yeah. This you leave 0 because it doesn't matter for this part because they're all just holes. This would be if you had like it shows there, if you had like a hard corner, you'd set that to the same diameter as your tool. Passes, you'll want to change this to 0.070. That's basically that determines how much of the tool is going to be engaged at one time. This you can just leave as normal. This multiple depths, we're not going to use it for this part, but if you wanted to, this would be like for if you wanted to take this in multiple passes in the Z. So if we were, drilling through, I don't know, like half-inch plate or something, you wouldn't want to take that whole bore all at once. You wouldn't want to plunge down half an inch and start routing out the hole, because that would probably break your tool. You'll want to do it in like 1/8 inch or 3/16 inch passes. So that gives you the option to do that, is how deep you want to go every time, or how many finishing passes you want to do. Usually we don't do any finishing passes, but how many steps do you want to do? And then you can even define, like on a face, you can even define like a slope angle, so you can make like angled holes if you wanted to, or angled pockets or cavities, or like they have in that example, looks like it's just an angled cavity. But we don't need that for today. Stock to leave, make sure you set this to 0. This is really important that this is 0, or all your holes are going to come off different. Basically what this means is you're going to leave some material for another operation to come by and pick up later. If we wanted to get really, perfect smooth finishes, that's what we do, but we get good enough finishes as is, just with the machine not taking those passes, so that's okay. Next, for linking, this is the last step here, and it's really not that more complicated than the rest. You're going to switch this to always use high feed and set it to be not 1,000 but 150 IPM. If I could use my keyboard, 150. Keep everything else basically the same. Keep tool down. The 2 inches is fine. Yours might be different on default. I changed mine, so keep 2 inches is okay. And lead in entry. These can all stay default right here. And now ramping. This is the important one. Now these holes are pretty small relative to our tool, right? Our tool is 0.157 and these are 0.20. That's only about what 43 thousandths difference between the two. So they're pretty small. We don't have room for this helix, right? Because this helix already has a diameter of 0.149. Right? If I could show you what that looks like. Does it give me a preview or something on one of these? Yeah, okay, cool. So if you look at helix, right, I can't move my mouse, but the bottom right, second column on the bottom, it'll ramp in doing like a helical motion. And that helix is already a larger diameter than our hole, so it won't pick up any of these holes. If we left it at this and we said, all right, yep, that's our operation, it would generate the tool path and nothing would happen. We should see tool paths right now, but we don't, because it didn't get any of these features because our helix is too big. So we'll go edit. It'll pick up all those surfaces again, and we'll go here and say to plunge. We'll plunge this time. And okay, cool. Yeah, that looks good. Stock to leave, again, 0. And now we should see toolpaths, just like that. So, there we go. That's one side done. And then, so we'll just do the one side, because the side is basically identical, and this video is already 20 minutes long. 25 minutes long, holy crap, okay. So the last step would be simulation. So we're going to simulate Now, what this lets you do is it lets you simulate what this would do on the machine, which is pretty cool. So we can show the stock, right? So that's what it would look like. It wouldn't be solid, but you know, it's not that super. It doesn't matter all that much. And we can hit play, and we can watch what it's gonna do. It's gonna clear out those, and we can set this to very good, so it actually looks like a decent. We can see that it's gonna go and it's gonna plunge down and clear out every single one of those holes, one by one. And we can even see down here how long is it gonna take. Oh, it's gonna take 2 minutes 32 seconds. This whole operation is gonna take 2 minutes 30, and we can skip around and speed it up, slow it down. See any pause it, play it, go to the next step, go back a couple steps if you wanted to, go back to the beginning, and then this is all you can check your preferences if you want to do something different. You can show only certain toolpaths or show only certain parts about the stock and things like that, or statistics. It takes 2 minutes 30 seconds. The total distance traveled is like 3.5 yards. Woohoo, whatever. I think you can actually change it to show different statistics too in some config file somewhere. But yeah, that's that. And you simulate, and then the absolute last step is to post process. So we would hit post. You would change this, or you change this output folder to the work folder on the workbench, which Zach will make and show you guys all where it is. So you'll all post to there. Even the cam guys in the shop that are watching this, you'll all post to that folder, to the CAD folder. And anyone who in CAD who feels comfortable doing this will also post to that folder so that our operators don't get confused. And for the program name, we'll come up with a naming system for it. So, no one will get confused on which part's what. But what you have to do change is in this post configuration, you change this achromatic, general achromatic. You got to go down to the M's, M, and pick Mach 3 mil.cps right there. And then you have to change this built-in high feed mapping to always use high feed. That's one of the important ones. That's the one thing you have to do. Leave everything else the exact same. Exact same. Don't touch any of this stuff. And then just hit post. And then you name it, because we didn't name it in the thing. If you had named it in the config, it wouldn't have asked you to do this, but we'll just name it test.tap. And that's it. You're done. You've created your part from start to finish. You have cammed it. Oh, and this will actually open up. This is what the code looks like. This is what the machine will be doing for 2 minutes 32 seconds. Yeah. So this is what the code looks like. Pretty cool. And we can go to line and block numbers and stuff. This is probably a bit over some people's heads, but you're welcome to read about it. It's an industrial standard, so when you use it here, you can use it anywhere, and we can always change stuff too. Like if I want my spindle to be going the other direction, I can change it to M4 and it'll go the other direction, but we don't want that, so we'll keep it M5. Don't mess with this stuff usually in case you really, 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 really painfully know what you're doing. Like seriously, this is complex stuff and it's easy to make mistakes. But yeah, so that's that. I hope you guys enjoyed this, and get back to work.